Okay guys, welcome back. In this video, we discuss choosing the appropriate test. So let's say you're given a bunch of infinite series. You're not in the section on ratio and root tests, so you don't know that you're supposed to use ratio and root tests. They're just asking you, determine whether the series converges or diverges. Well, we've got 10 tests to choose from. I just wanted to give you a checklist. This is my approach. Some people use a slightly different approach. Some people put these questions in a different order. But this is the order I tend to ask them when I'm looking at a series. So I'm going to go through this list with you, and then we're going to look at 10 infinite series and choose the appropriate test, and then determine whether each of the series on our list converges, well, each series converges or diverges. Yes, that's proper grammar. Okay. So the first thing I ask myself when I'm given a series is it geometric or a p-series? Those are the easiest ones to evaluate, to determine whether they converge or diverge. You just look at R, you just look at P. If the absolute value of R is less than 1, the geometric series converges. If P is greater than 1, the P series converges. So if it's a geometric series or P series, use that test. Then the next one, sometimes I skip. If it's obvious when I look at a sub n that its limit is not 0, then I immediately use the nth term test for divergence. Now, if it seems to me that computing that limit might take a little bit of time or thought, I'll skip right over this one. But if it's obvious, maybe I've got a rational expression with the same degree in the numerator and denominator, and I can just read off the coefficients and I know that this limit's not 0, then I would use the nth term test for divergence. If the series is telescoping, then I use the telescoping series test. I especially would use this test if I'm interested in finding the sum of the series. If the question isn't just, does this converge or diverge, but instead the question is, this converges, what does it converge to? If it's telescoping, I want to use this test. Now remember, you can recognize a telescoping series if it has this form, or it can be rewritten in this form. So what you see is the same function here and here. One is evaluated at n plus k, the other one is evaluated at n, and they have opposite signs. If that's true, when you look at the partial sums, like s sub 1, s sub 2, s sub 3, you're going to see some cancellations because of that positive and negative here, and the fact that this one is evaluated at n plus k and that one's evaluated at n. Now sometimes you have an f of n minus f of n plus k. The order really doesn't matter. The key here is that you've got the same function evaluated at n and n plus k, and they have opposite signs. If that's true, the series is telescoping, so you'll find the formula for the nth partial sum and you'll compute its limit as n goes to infinity. Now, if the series was not geometric or a p-series, but it looks like one, you're saying, gosh, if that 1 wasn't there, if that 3 wasn't there, if that plus n wasn't there, this would be geometric, or this would be a p-series. Then I go to the comparison tests. I always start with the direct comparison test, and if that doesn't work, I go to limit comparison. But if it looks like a p-series or a geometric series, but it's not one of those, I try the comparison tests. Then next, I usually ask about the alternating series test. If I see that I've got a negative 1 to the n, or some other alternating expression, negative 1 to the n plus 1, negative 1 to the n minus 1, something like that. If I see that my series is alternating, if I'm not interested in absolute convergence, I just want to know if the series converges, I will use the alternating series test. Okay. Then if you have a quotient or a product, and it's not a p-series or a geometric series, so maybe the nth term looks like a hybrid of terms of geometric series and p-series. So you've got numbers raised to powers and n raised to a power, and that power is a number. So you see things, just for example, you might see something that looks like that as part of your nth term, and you might also have something that looks like that as part of your nth term. So that looks kind of geometric, and that kind of looks like a p-series. But if your nth term has both, you might use the ratio test, or if your nth term involves a factorial, the ratio test will work well. And the reason why the ratio test works well in those cases is a sub n plus 1 divided by a sub n, when you're computing that limit, the limit of that as n goes to infinity, if a sub n involves factors like this and this, or if it has factorial in it, this will be very easy to simplify using standard properties of exponents and limits at infinity, properties of rational functions, and our techniques for evaluating limits at infinity. So if any of these is true, this limit is pretty easy to evaluate. So I would use the ratio test. Now, if a sub n looks like one of these, so it's some expression raised to the nth, or maybe a constant over some expression raised to the nth, we'll use the root test. Because when you take the nth root of this and the nth root of this, that nth power just goes away. The nth root of c is c to the 1 over n. That's going to approach 1 as n goes to infinity. So yeah, I would use the root test if it looks like this. And then lastly, if none of these other ones work, and replacing the n's with x's yields a function that's easy to integrate, I might use the integral test. Now I tend to use this test last because I have to check the 3 conditions of the integral test. I need to show that f is positive, continuous, and eventually decreasing. It's a lot of work before I evaluate an improper integral. Usually one of these other tests at the beginning works better than the integral test. It's more efficient at getting to my answer. But worst case scenario, you can always go to this, provided that it's integrable. You can't do anything about that factorial. So yeah, that's my approach. Let's actually apply it to determining whether some series converge or diverge. So I've got my list over here, and I want to look at all of these series. I've got a list of 10 of them. I'm just going to put one at a time on this second sheet of paper. I guess it's a third sheet of paper, that's okay. Now let's go through our checklist. Is it geometric or a p-series? No, it's not geometric or a p-series. Now, it's not obvious how this behaves as n goes to infinity. It turns out that as n goes to infinity, a sub n approaches 0, so the nth term test tells us nothing, and it's definitely not telescoping. So the next thing we would try is the comparison tests. It's not geometric or p-series, nth term test doesn't apply, it's not telescoping, so let's compare this to something. To me, this looks a lot like 1 over 3 to the n. And 1 over 3 to the n can be rewritten as 1/3 to the n using our exponent properties. So this is a very good candidate for the comparison tests. Now some students say, oh gosh, what do I do with that cosine of n? Cosine of n and sine of n are your friend when it comes to the comparison tests. Cosine and sine, remember the y values on those graphs always lie between -1 and 1. So before I even write down the inequality for this, I can write down this inequality. I know cosine of n is between -1 and 1. And I don't have to use the less than or equal to signs because n is a positive integer, and we know cosine is going to approach, it's going to be -1 and 1 at multiples of multiples of pi. And this is never going to be a multiple of pi. We're never going to have an irrational number here. So cosine of n is between -1 and 1. You might say, well, what is that? How does that help me? Well, I can manipulate this inequality until 1 plus cosine of n over 3 to the n is in the middle here. So first of all, I need a 1 plus that. So I'm going to add 1 to all 3 parts. So if 0 is less than 1 plus cosine of n, and that's less than 2, and I'm trying to make this middle expression look like my nth term, look like this. So I'll divide all 3 parts by 3 to the n. All right, and of course 0 divided by anything is just 0, except for 0. I've got my nth term in the middle, And then over here, I could rewrite that. 2 over 3 to the n is the same as 2 times 1/3 to the n. And if you don't believe me, you should expand that. 1 to the n is just 1. 3 to the n, of course, will stay in the denominator. It's 3 to the n. If I write this as 2 over 1 and I multiply straight across, I get this. So this is equivalent to that, and we're right here. So I'm able to compare this to this geometric series, and I knew that that was coming. I knew I could compare it to a geometric series because cosine of n is always between -1 and 1, and if I ignore that part, it looks like a geometric series. So you'd say, okay, well, now you're going to use the comparison test. Both of these guys are positive, and I've got a geometric series, so I know whether it converges or diverges. So let's see if we can conclude anything about this guy over here. So we'll say since this series, yes, those parentheses weren't necessary, but that's okay, I just started writing them. This series is a convergent geometric series because, and we know it converges because r is 1/3, and the absolute value of 1/3 is 1/3, and that is less than 1. Since this is a convergent geometric series, or these are the terms of a convergent geometric series, I add all of these together and I get some finite number. I can actually figure out what that number is. But if these are smaller, if I add all of these together and I got 20, and these are smaller, I should be able to add all of these together and get something that's less than or equal to 20. So the direct comparison test is appropriate here, and we'll say since this one converges, this one converges. And I will use the abbreviation DCT for direct comparison test. Okay, because it looked like a geometric series, but it wasn't a geometric series. And we used this fact that cosine of n is between -1 and 1. Another fact that you might use later when you're using the comparison test is that sine of n is always between -1 and 1. So keep that in mind when you're working problems. Sometimes those come in handy, and they allow you to compare something like this to the terms of a geometric series or the terms of a p-series. Okay, so that was our first one. Let's look at the second one. Now on the surface, this might look like it's not a good candidate for the comparison tests, but it actually is a good candidate for the comparison tests because of another fact that we really haven't talked about much in this class. But I'll show you the graph of natural log of x. Y equals natural log of x looks like this. It has a vertical asymptote at x equals 0, and as x goes to infinity, natural log of x goes to infinity, but it goes to infinity very slowly. The slope is always 1 over x. So when x is 100, the slope is 1 over 100. It's increasing, it's always positive, but it's a very, very small positive number, that slope is. So it almost looks like it has an asymptote, but it doesn't. It's just slowly, slowly going to infinity. So this is y equals natural log of x, and y equals x is here. It's obvious from these graphs that x is always greater than natural log of x. Or if you want to write it the other way, natural log of x is always less than x. Well, if that's true, if I evaluate these functions on the natural numbers, so I evaluate them at 1, and I evaluate them at 2, and I evaluate them at 3, and then 4. all of these values are going to be greater than all of these values. So if natural log of x is less than x, then I can automatically say natural log of n is less than n. Because those n's are just special cases of those x values. X could be any real number. We're just saying those n's are natural numbers. Okay, so you might say, well, what does that have to do with anything? It has a lot to do with this particular series. So this is just another fact that we have. Okay, well, let's look at this guy. Well, notice I've got a natural log of n in the denominator, and I'm taking the natural log of n. So the first thing I would do to write down an inequality for this is I would use this fact. I know that natural log of n is less than n. Well, if this is true, turns out I can take the natural log of both sides of this inequality, so I have the natural log of n, that's going to be less than the natural log of n. And natural log of n from over here is less than n again. Saying, why are you doing this? Well, let's see. Now I've got an inequality that describes denominators. I know that natural log of n is less than natural log of n, and that's less than n. And here's another fact, one that we've used many times before. If the numerators are the same, but the denominators are larger, so let's say you're just comparing 1/3 and 1/2. If I take 1 and I divide it into 3 pieces, that's going to be smaller than if I take 1 and divide it into 2 pieces. So provided the numerators are the same, if you have a larger denominator, the fraction is smaller. So we write that down. When the numerators are the same, a larger denominator implies a smaller fraction. So that's a fact, a handy fact that we're going to use right here. So we have like 3 is greater than 2, so 1/3 is less than 1/2. So we're going to take reciprocals of all of these guys. But what that will do is it will flip the inequalities. Since n is larger than this, 1/n is smaller than this fraction. Since this is larger than this, 1/this is smaller than this fraction. And of course, if n is starting at 2 and going to infinity, all of these guys are positive. So now I've got an inequality, and I'm all set for the comparison test. Without this one, you might say, okay, that's a good comparison, but the problem is I don't know how this one behaves. We only want to use the comparison test when we can compare the terms of our series to the terms of a p-series or a geometric series, or one that's very easy to determine the convergence or divergence of. So I wouldn't stop here because that's not going to get me anything. If I use the comparison test now, if this one converges, this one may or may not converge. Like we can talk through what all the possibilities would be. But I guess my point is, if you don't know whether the series you're comparing to converges or diverges, the comparison tests don't help you. So you need to compare it to something, or compare it to the terms of something whose convergence or divergence you know. So we needed to go all the way out to here to 1/n, because that's a p-series, or those are the terms of a p-series, with p equals 1. And of course, p equals 1 is less than or equal to 1. So those are the terms of our harmonic series, that series diverges. So, okay, does that tell us anything this time? Well, these are larger. So if this series diverges, I add all of these up and I get infinity. Well, if these are larger and these are larger, if I add these up, I'm going to get infinity as well. And if I add these up, I'm going to get infinity as well. So the inequality is in the right direction to tell us that all three of the series that correspond to these terms diverge to infinity. So let's use the direct comparison test to state our conclusion for this guy. We'll say since this series is a divergent p-series, p equals 1, which is less than or equal to 1, this series diverges to infinity as well by the direct comparison test. Okay, so that's one where it might not have been obvious that a comparison test was appropriate, but because I knew this fact, because I knew I could always compare natural log of n to n, I knew that the comparison test would be appropriate. Now, if you're saying to yourself as a student, Miss Townsend, I would have never thought of that, I agree and I understand. I don't think I would have, well, I probably would have thought of that, but only because I had studied these functions a lot. I really wouldn't expect most students to have thought of that if you hadn't studied these functions for a while. But now that I've told you, you know that this is a fact that you can use. And you know that this is a fact that you can use, and you know that these are two facts that you can use. And those are going to allow you to use your comparison tests a lot more often than you would be able to use them otherwise. Okay, so now let's look at this next one. Now, the first thing I always ask myself is it a p-series or a geometric series? Well, it's not a p-series because it doesn't have an n to the p, but I think it is geometric, even though it's not written in the right form yet. With exponent properties, I should be able to write this as a constant to the n. And I should be able to write this as a constant to the n times a 5. So this is geometric. If you want to determine the first term and the common ratio, the thing that you multiply by to get from term to term, you can just substitute in n equals 1, n equals 2, n equals 3, and then you'll see what the first term is, what the common ratio is, and you'll see that that pattern seems to continue. If you want to prove to yourself that that works, you could also just, or if you want to prove to yourself that the common ratio r is of a certain form, rather than doing that, which would just sort of imply that r is probably that, we could use exponent properties to rewrite this. So rather than doing what I just mentioned, like writing out the first term, writing out the second term, and looking for the common ratio, I'm just going to do a little bit of algebra to write this in a different form. So here are the techniques from algebra that we need to rewrite this so it looks like a constant times a constant to the n. Because remember, our geometric series has this form, a constant times a constant to the n. And if we want a to be the first term to be something that we can just read off, we would have to start the summation with 0. This one starts at 1, so we're not going to be able to read off a. Okay, so let's go through our exponent properties. If you've got something raised to a power, you multiply those exponents. So I can use that to rewrite this guy. Down here, I've got something, or a base raised to a power times the same base raised to a different power. Turns out you just add those exponents. So with both of those rules, and one other rule, if you have a to the n over b to the n, you can write that as a over b to the n. With those three rules, we should be able to write this as a constant times a constant to the n. And whatever that constant is that you're raising to the nth power, that's your common ratio. So we're just going to do the algebra. If you want, you can write that as a negative 1 to the n times a negative 1 to the negative 1. Just puts a negative 1 in the denominator. Over here, I've got a 3 to the 4n. According to this rule, I can break that up and call it 3 to the 4th raised to the nth. Down here, this is going to be a 5 to the 3n, times 5 to the 1st because of this rule. We're adding those exponents, so it's going to be x to this power times x to that power. So x to this power times x to that power, and that's what I've written here. That 5 to the 3n can be rewritten using this rule. So I've got -1 to the n, and that's just a -1 in the denominator. That -1 times that 5 is going to give me a -5. 3 to the 4th is 3 times 3 times 3 times 3, so it's 9 times 9, or 81. And then down here, that 5 to the 3n, I can write as a 5 cubed to the nth. And of course, 5 cubed to the n is 125 to the nth. Now I've got that to the nth, that to the nth, and that to the nth. With this property and another property, this property, I can rewrite these guys. If you have something to the n times something else to the n, we can multiply those somethings. That's what that rule says. And I still have that -5 in the denominator, so I could factor it out as a -1/5. And the numerator, I've got a -81. And then because of this rule, I've got -81 to the n over 125 to the n, so I could call that -81 over 125 raised to the nth power. Okay, so this looks like a times r to the n. It's not exactly a times r to the n though, because the index starts at n equals 1. Now we could change this to a 0 as long as we modify that. There's a way to rewrite this so that the index starts at a different number. That's one approach to finding a, or you could just substitute in n equals 1 and get your first term. So now we know it's a geometric series. We've rewritten it as a constant times a constant to the n, and r is the number that's being raised to the n. So r is this -81 over 125. So we'll say that since the absolute value of r is 81 over 125, which is clearly less than 1, the geometric series converges. Now, if you have a geometric series or a telescoping series, those are some of the few series whose sums we can find. So let's find the sum of this series by identifying the first term, and we already know what r is. So I'm going to use the next page to find the first term. The first term is just this expression evaluated at n equals 1. And then, of course, when n equals 2, we get the next term. And so on. So this is a. That's our first term. So the sum of the series is our first term, which is traditionally called a, over 1 minus the common ratio. And that first term simplifies to 81 over 625. In the denominator, we have 1 minus the -1 over 125. And we could practice adding and subtracting fractions and dividing fractions, but I'm just going to use a calculator so that we don't spend our whole calculus video doing arithmetic. And so we get 81 over 1030. That's the sum of the series. If you add up all of those terms, you're going to get that. Okay. Or that's what the sequence of partial sums approach is, if we want to be more precise. Okay. Now in this next one, you might think this is a hard one, but it's actually an alternating series. And it's just another fact that we need in order to show that it's alternating. You're saying, what? Why is it alternating, Miss Townsend? It's alternating because of that cosine of pi n. So let's look at cosine of theta or n. So it looks like this. When n equals 0, we're right there at 1. When n equals 1, we've got cosine of pi. So I didn't do a very good job with my graph. That's negative 1. Then when n equals 2, we've got cosine of 2 pi. 3, we're here. 4, we're here. 5, we're going to be there. 6, we're going to be there. And so on. You see what's happening? Cosine of pi times n, or n times pi. I don't know why I put it in that order. Well, it's negative 1 to some power, because it's alternating between negative 1 and 1. The question is, which one is it? Is it negative 1 to the n, or negative 1 to the n plus 1? Well, when n equals 0, we get a positive number. So I think that's going to work. When n is 0, we get cosine, or negative 1 to the 0, which is 1. When n is 1, we'll have cosine of pi. So we have negative 1 to the first, which is negative 1. That's what it's supposed to be. So here's a fact that you can use. You can recall and use again. With that fact, well, we see that this is just the alternating harmonic series. And the alternating harmonic series converges. It converges conditionally, and we did that in another video. But just briefly, let's practice applying the alternating series test. B sub n is the absolute value of the nth term. So that's just 1 over n. And we need to check two conditions. We need to look at the limit as n goes to infinity of b sub n, which is the limit as n goes to infinity of 1 over n. As n gets very large, the fraction gets very small, and as this gets larger and larger, this gets smaller and smaller, so we get 0. And if I look at b sub n plus 1, and I look at b sub n, and remember how you find b sub n plus 1. You just replace the n's with n plus 1, so you get this. The numerators are the same. And this one has a larger denominator, so I'm taking 1 and I'm dividing it into more pieces. It's a smaller fraction. So I can write this. That's true for all n, all natural numbers n. Okay, so the first and second condition of alternating series test are satisfied. So that means our alternating harmonic series converges by the alternating series test. And again, we're using this fact. Cosine of pi n, or n pi if you prefer, is negative 1 to the n. Okay, now let's do another one. Do you know what test to use here? Well, is it geometric or a p-series? No, I don't see a constant times a constant to the n, and I don't see an n to the p power, where p is a number. So it's not one of those. What about the nth term test? As n goes to infinity, do I get something other than 0 here? As n goes to infinity, this approaches 0 and this approaches 0. So I've got cosine of 0 minus cosine of 0, so 1 minus 1, which is 0. So the limit of the nth term is 0, which tells us nothing. So that's not going to work. But notice that these functions are pretty much the same. I've got a cosine of 1 over n here and a cosine of 1 over n plus 1. And the only difference is that this one has an n in it and this one has an n plus 1 in it. So this is a telescoping series. They've got opposite signs. You've got the same function evaluated at n and n plus 1. So I'm going to use the telescoping series test. And when we do that, we should be able to determine what this converges to. Now remember, this is a sub n. It's not s sub n. Oops, I just labeled it exactly the wrong way. That's a sub n, not s sub n. So that's the first term. Now s sub 1, that's the sum of the first term and nothing else, I guess. So we've got cosine of 1 over 1 minus cosine of 1 over 1 plus 1, so cosine of 1/2. So you have cosine of 1 minus cosine of 1/2. And of course nothing reduces yet because we haven't added terms to it. Now s sub 2 is the sum of the first two terms. So you take what you just had, that cosine of 1 minus cosine of 1/2, and then you add what you get when you replace n with 2 up here. So we'll have cosine of 1/2 minus cosine of 2 plus 1 is 3, so it's going to be minus cosine of 1/3. Well, notice what happens. The cosine of the negative cosine of 1/2 and the positive cosine of 1/2 reduce, and you just end up with two terms again. We had two terms here, and then we had two terms here after cancellation. And that's what we told you would happen with telescoping series whenever those functions are the same but with opposite signs, and you have the n and the n plus k and all that jazz. So we'll just keep going. S sub 3 is the sum of the first three terms. And the reason why I'm doing this is I'm trying to figure out what the pattern is. So I just write down my a sub 1 plus a sub 2. I did that on the last step. And then the next thing I do is add in a sub 3. So I replace n with 3 in this. So it gives me cosine of 1/3 minus cosine of 1/4. And we simplify. So these guys are the same but with opposite signs, so they reduce. These guys are the same but with opposite signs and they reduce. So I end up with two terms again. So I think we're ready. We're ready to write down our nth partial sum. The first thing I want to write down is everything that stays the same. As I go from term to term, is there anything that they all have in common? Well, look, s sub 1 has a cosine of 1 in it, and s sub 2 has a cosine of 1 in it after the cancellations. S sub 3 has a cosine of 1 in it. And I know we're getting some cancellations over here. I'm never going to get a minus cosine of 1 on this side. It's just not going to happen because we keep getting a 1/2, then we have a 1/3, the next one's a 1/4, the one after that's going to be a 1/5. We're never going back to 1 over 1. So that guy's going to stay. I'm keeping the cosine of 1. Now I want to look at what's changing as I go from term to term. And it looks like I still have a cosine of something, and cosine of something, but those denominators are changing. So I'll say this is going to be minus cosine of 1 over something. That's the same. But then I want to look at this denominator. I've got cosine of 1/2 and cosine of 1/3 and cosine of 1/4. And I want to think about that number that's changing, 2, 3, 4, and how it relates to the subscripts over here, 1, 2, and 3. When that's a 1, that's a 2. When that's a 2, that's a 3. When that's a 3, that's a 4. So it looks like this is always one more than this. Let's check. Is 1 plus 1 2? Yes. Is 2 plus 1 3? Yes. Is 3 plus 1 4? Yes. So if this is n, this should be an n plus 1. Okay, so with telescoping series, the first thing you do is find s sub n, and we did, and then you take the limit of this as n goes to infinity. And if that limit exists, that's the sum of your series, because that's the definition of the sum of a series. It's the limit as n goes to infinity of that s sub n, that nth partial sum. Or you could say it is the, well, it's not just the limit of s sub n. The series converges if the sequence of partial sums converges. And if this limit is finite, that's telling us the sequence of partial sums converges to that number. So we're taking the limit as n goes to infinity of cosine of 1 minus cosine of 1 over n plus 1. Oops. And as n goes to infinity, this is 1 over something very large. That's very small. So we have cosine of 1 minus cosine of 0, and cosine of 0 is 1. Now, Calc 2 students are often very tempted to simplify this cosine of 1. That does not simplify nicely. You're just plugging in 1 to the cosine function. It's not a special number. 1's not a special angle. So it doesn't simplify. But that is the sum of our series. So we could write that this series converges to cosine of 1 minus 1. Or we could say this series equals cosine of 1 minus 1. All right. So that was we did 1, 2, 3. This is our 4th example, and then this is our 5th example. I think I have 5 more on my list. I don't think we're going to be able to do all of them within the hour. But let's talk about these other guys over here and which tests are appropriate. So on each of these, I would ask myself, okay, is it geometric or a p-series? No. What about the nth term test for divergence? Well, as n goes to infinity, I believe this goes to 0, so that won't work. It's not telescoping. Does it look like a p-series or a geometric series, though? Well, kind of. As n goes to infinity, that 8's not going to matter very much, and that negative n is very small compared to that n to the 5th. If n is 1,000,000, that's 1,000,000 to the 5th, and that's a minus 1,000,000. Minus 1,000,000 is not so big compared to 1,000,000 to the 5th. So yeah, I think that this is comparable to a p-series. So I would compare this one to a p-series. And you say, which p-series should we compare to? Remember, you want to keep the terms that dominate in the numerator and denominator. So I want to keep between the 3n squared and this n to the 1/2 power, because that's what that is. I want to keep the one with the larger exponent. So I'm going to keep the 3n squared term. And in the denominator, the 2n to the 5th dominates. The negative n doesn't matter much. The 8 doesn't matter much. So I would compare to a p-series with these terms. And you might say, technically it's not a p-series. You're right. It's a multiple of a p-series. I'll just take the square root of that, and the square root of n to the 5th is n to the 5 over 2. And if you subtract, that's going to give me an n to the 1/2 in the denominator. So we're going to compare this to this. I'll call this my a sub n, and I'll call this b sub n. Now, it's probably not obvious which way the inequality goes in this case, I can't just immediately say, oh, the denominator is larger, so the fraction is smaller because of this. We've got a minus and a minus and a plus. We've got a lot of interest, or a lot of things going on here that make that inequality not something that we can definitely say is true all the time. So I would use limit comparison test, where this is my a sub n and this is my b sub n. But I'm doing that because it kind of looks like a p-series. Don't be distracted by all this extra stuff. As n goes to infinity, that's not going to matter much, and we're going to end up with something that looks like that. Okay, now in this one, well, it's kind of like what we did over here. This one is a p-series, or a multiple of a p-series. We just need to do a little bit of algebra. So I would factor out the 2/5, so you can see that it's a multiple of the p-series. Call that an n to the 1/2 in the numerator, and an n to the 3/2 in the denominator is already there. Then subtract the exponents. You'd have an n to the -1, or you could rewrite that as 1 over n. So this is a multiple of the harmonic series. P equals 1, which is of course less than or equal to 1, so the series diverges. Oh, my neighbors are banging on the wall. It startled me a little bit. Okay. Now, I've got this series, and this series. Saying, okay, which tests are appropriate here? Is it geometric or a p-series? No. What about the nth term test? This time the nth term test is promising, because you've got the limit of a function of n, or excuse me, the sign of this function of n, and as n goes to infinity, well, that's a 3 pi times n, and that's a 2n plus 1. The degree of n in the numerator and denominator is the same. So even though this is an infinity over infinity indeterminate form, I expect to get 3 pi over 2. What's the sign of 3 pi over 2? Well, it's not 0, that's for sure. If you remember your trig, you know that that's -1. So this would diverge by the nth term test for divergence. And I'm just going to write, because the limit as n goes to infinity of a sub n is -1, you should check that out for yourself. Make sure that you agree that that's true. Okay, last two guys. Last two series. Is it a geometric series or a p-series? No. Is it telescoping? No. What happens as n goes to infinity? Or excuse me, yeah, as n goes to infinity. I'm pretty sure that this goes to 0. So that test is inconclusive. Also, with the nth power, you're like, I'm not really sure. Don't worry about it then. Skip it if it's not an obvious limit. Is it comparable to a p-series or a geometric series? Well, maybe, except for that nth power. But remember what we talked about before. If you have a function raised to the nth power, the root test is appropriate. So on this one, I would use the root test. You're going to take the limit as n goes to infinity of the nth root of the absolute value of a sub n, and that's just going to get rid of that nth power, and we get something that looks like this. Whoops. That's an infinity over infinity indeterminate form, but natural log of n grows very slowly. It grows much more slowly than this 2n cubed. So this is going to be 0 after switching from n to x and using L'Hopital's rule. We can show that that limit is 0. Now when we're using the root test, if we get a limit that's 0 and that limit is less than 1, that means the series converges absolutely. So we're good there. And then with this last one, it is the ratio test, and I know to use the ratio test because of the factorial. Let's do that ratio test. I know we did these guys kind of quickly, but I just wanted you to show I just wanted to show you the procedure for how we determine which test is appropriate. I'm also going to give you those 30 practice problems and all of the solutions on our course website. So stay tuned for that. That way you can practice determining the appropriate test, choosing the appropriate test, and then applying them. When more than one test applies, you can use whichever test you like to determine whether a series converges or diverges. There might be and often is more than one way to get the correct answer. But I would like you to get in the habit of trying to determine the most efficient way, because I don't want you to waste too much time integrating something when you could have used a simple comparison test. So I will give you those problems and all the solutions for you to practice with very shortly. Now let's just do this last ratio test as practice. And then we'll be done. We'll be done with this video. The sum as n goes from 1 to infinity of n to the 3n over n factorial. That's our a sub n. And remember, a sub n plus 1 just comes from replacing all of the n's with n plus 1. So I have a sub n plus 1. This will be an n plus 1 to the 3 times n plus 1. In the denominator, we've got n plus 1 factorial. And of course, you could distribute that 3 in the exponent, so that's n plus 1 to the 3n plus 3, all divided by n plus 1 factorial. Okay, so we're going to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, because we're using the ratio test, and we chose to use the ratio test because we had a quotient and it had a factorial in it. So we'll take the limit as n goes to infinity of a sub n plus 1. I'm going to write that down. Now the absolute values are not necessary here because the terms of a sub n plus 1 and the terms of a sub n are already positive. Absolute value of a positive number is just itself. So I can just write down a sub n plus 1 here, and then the reciprocal of a sub n over here, and then we'll multiply. Because dividing by a fraction is multiplying by the reciprocal. So we take this guy, we flip it and multiply. And then we want to regroup using the commutativity of multiplication. We can multiply in any order we want. So I can write this in the numerator. Instead of this times this, I can write it as that times that. So I'll put the n factorial first, and I'll put it over the n plus 1 factorial. And over here, I've got an n plus 1 to the 3n plus 3. And I will divide that by n to the 3n. Okay, now the factorial expression can be simplified, and then this expression can be simplified using exponent properties and just properties of algebraic expressions. So over here, we want to expand the one that has a larger number that you're taking the factorial of. So the n plus 1 is larger than the n. And remember how factorial works. You start with n plus 1, and then you subtract 1. You multiply by 1 less. N plus 1 minus 1 is just going to be n. And then we multiply by 1 less than that and 1 less than that. So after you take out the n plus 1, you're left with an n factorial. In the numerator, you also have an n factorial. So those guys reduce. Now over here, I want to use my exponent properties again. If I have x to some power times x to a different power, well, we can add the exponents. We can also use this rule backwards. So if I have a 3n plus 3, I can call that n plus 1 to the 3n times n plus 1 to the third using this rule in reverse. Now I notice I've got an n plus 1 here and an n plus 1 cubed here. So one of those will reduce. Now I've got an n plus 1 squared there. This really doesn't look like these terms anymore, so I'm going to factor it out. And notice that these exponents are the same. So I'm going to use this property. If you've got a to the n over b to the n, you could write that as a over b to the n. So let's write that as n plus 1 over n to the 3n. And of course this can be simplified. N over n is 1. 1 over n is still there. And this 3n can be written differently. It can be written as something to the n, that expression to the n, all cubed, because of this property. If I take something and I raise it to a power and then I raise it to a power again, I multiply those exponents. So I can sort of do that in reverse. If these exponents are multiplied, I can make this, or I can take this expression, which simplifies to this, and I can raise it to the n and raise that to the third. Because n times 3 is the 3n, and then this is just the simplified version of that. You might be saying, Ms. Townsend, why did you do that? Well, it's because of a fact I'm aware of. As n goes to infinity, this approaches 0, and so I end up with a 1 here, and this approaches infinity. That's a 1 to the infinity indeterminate form. Back in Calculus 1, when you were studying L'Hopital's rule, you learned how to get rid of those 1 to the infinity indeterminate forms. We took the log of both sides. It was relatively involved, but we were able to show that as n goes to infinity, this expression approaches e. And you're like, what? What does that have to do with anything? It's surprising, but it approaches e. So this is approaching e cubed, and as n goes to infinity, this is obviously approaching infinity. A large number plus 1 is still large. I square it, it's still large, and then I multiply by 2.7 cubed. And it's very small, or not very small, but it's insignificant, just multiplying by a number. So yeah, we get infinity. And what does that tell us? Well, the limit is greater than 1, so the series that we started with diverges to infinity by the ratio test. Okay guys, that's it for this video. Here are our tests. Ask yourself, is it geometric or a p-series? If so, use that test. Is it obvious that the nth term is approaching a number that's not 0? Then use the nth term test for divergence. If computing that limit in your head is too much, go ahead and skip that one. It's not going to be the most efficient way. Does a series look like this? So you have the same function twice. One of them is evaluated at n plus k. One of the functions is evaluated at n. They've got opposite signs. One's positive, one's negative. Then it's telescoping. Or if it can be rewritten to look like this, it's telescoping. Then you use the telescoping series test. Then you say, okay, if it looks like a p-series or a geometric series, but it's not a p-series or a geometric series, let's compare it to one of those. Try direct comparison first. If that fails, use limit comparison. If it's alternating, you might want to try the alternating series test. Now, if your a sub n is a quotient or a product, or if it looks like, if the terms, the factors of a sub n look like a hybrid between those of a geometric series and a p-series, so you see numbers raised to powers and n raised to numbers, or if it has a factorial in it, the ratio test is a good option. If your nth term can be written as a function to the n, or a constant over a function to the n, the root test is a good option. Then worst case scenario, if you can replace the n's with x's and it looks like something that's easy to integrate, go ahead and use the integral test. So that's what I recommend. Please reach out if you have any questions as you try these problems at home. You will get better at it with practice.